So a quick review with the Bohr atomic model. Bohr says that the electrons in an atom exist in what we call stationary states. It doesn't mean the electrons are stationary. It means that they're in an energy state and the amount of energy that they have is not changing. It's a constant energy. If an electron makes a transition to a lower energy level, then a photon is emitted because the electron loses energy. If an electron makes a transition to a higher energy state, then a photon is absorbed. Fair warning, on a diploma exam, they tend to use the word jumps, whether it jumps up or down. I don't particularly care for that, but just because you see the word jumps on an exam doesn't mean it's going up. It could be going down. You have to read the question carefully. The energy of the photon involved is related to the change in the energy of the electron. So if you always take the upper energy level minus the lower energy level, you'll get the energy of the photon. You go upper minus lower regardless of which direction the electron moves. Just a couple of observations here. If you're missing the upper level and you know the lower level, add the photon energy to the lower level to take you up. And if you're missing the lower level, take away the energy of the photon from the upper level to find the missing energy level. Does anybody have any questions you'd like me to go over from this section? Ian? Okay, let's look at number 10. A mercury atom in an excited state has an energy of negative 4.95 eV. And if you take a look at the diagram, and I apologize for the diagram above that, I think it's calcium. Some of the lines are very close together and hard to read. But number 10, Ian, is saying that the electron is in the E4 state. And we talked a little bit about this, but it didn't come up a lot. I can say the electron is in the E4 state, or I can say the atom is in the E4 state. When I say the atom is in the E4 state, I'm just telling you where the electron is in the atom. It absorbs a photon so that it rises to the next highest energy level. And the next highest energy level, looking at that diagram, is E5, which is negative 3.71 eV. Now, you'll notice that this energy level diagram has both scales on it. It has a scale on the left that uses negatives, where 0 is at the top, and it has a scale on the right that uses positives, where 0 is at the bottom. The bottom line here, Ian, is that the difference between these two energy states, the difference between E5 and E4, is the change in the energy of the electron or the change in the energy of the atom, which means it's the energy of the photon. So to answer the first part of this question, all we need to do is take either 6.67 minus 5.43, which is 1.24 eV, which is the answer, or take negative 3.71 minus negative 4.95, which gives you 1.24. At this point in time, you know the energy of the photon that's emitted because that's the energy change of the electron, and I just misspoke. It's a photon that's absorbed, I think, because it tells you it starts at E4 and goes up to E5. Now what we can do is use our energy equals HF formula and put in Planck's constant, divide that 1.24 eV by 4.14 times 10 to the negative 15 and get the frequency. So hopefully we'll get 2.99 times 10 to the 14 hertz. Does that help? Okay. Any other questions before we move on today? All right, we have one more model of the atom we want to discuss today, and that's called the quantum model of the atom, or the quantum mechanical model of the atom. And we're going to use part of today as well to start applying physics to Bohr's model of the atom to describe what's going on in more detail. And we're also going to be applying physics in analyzing Rutherford alpha scattering with gold nuclei. And the reason why we don't have a lot of work to do with the quantum mechanical model of the atom and that we'll have time to do those other things is this model of the atom is really, really complicated. Okay, we can't even get into the formulas that exist for this. I'll talk about them briefly. But we want to look at the limitations of the Bohr model of the atom. We started with the Dalton model. The limitation of the Dalton model was that it didn't have electrons. So when electrons were discovered, Dalton's model had to be revamped. And that led us to the Thomson model. Thomson model of the atom was no good because it couldn't explain alpha particle scattering by gold nuclei or gold atoms. So it was revised to give the Rutherford model of the atom. The Rutherford model of the atom couldn't explain line spectra. There were some other problems with it, but I don't want to get sidetracked here. The basic idea is it couldn't explain line spectra, so Bohr came to the rescue. But there are limitations to Bohr's model of the atom. We're also going to be looking at the key features of the quantum model of the atom. And then, as I said, we're going to be looking at applying physics principles to the hydrogen atom and also solving alpha scattering problems using physics principles. And these are three totally different things. The quantum model of the atom is one kind of lesson today. And then we also have to look at these other two things at the bottom of the screen. So what are the problems with the Bohr model of the atom? Well, it's limited to atoms with one valence electron. So when you take a look at a periodic table, the Bohr model of the atom, well, I want to make sure you understand what I mean by limited. Niels Bohr was able to come up with formulas to find the energy level diagrams of all of these atoms. He could not come up with energy level diagrams for any atoms. However, I want to be very cautious here. This idea that electrons in atoms go from higher to lower or lower to higher energy levels and a photon energy is involved, that is true for all of the atoms. It's just that the energy levels don't have values in eV or joules that are easily found by Bohr. His idea is still right, but his formulas only work for those group 1A elements. There we go. And when I say limited to atoms with one valence electron, these are the atoms I'm talking about: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Cannot explain the relative intensities. If you were to flip back a few pages in your note package and look at the hydrogen bright line spectrum, or just go back in your memory, hopefully you'll remember that that violet line is very faint. One of the reasons why it's very faint is that our eyes are just not sensitive to that color of light. But there's another reason, and that's that there's just not a lot of violet light in that pinkish blend of hydrogen light. However, the red is more prominent, and that explains why when you mix all the colors together, you get a pinkish color. What that means is the transition that's occurring in hydrogen to produce red, which happens to be 3:2, happens a lot more often than the transition that occurs to produce violet, which happens to be 6:2. And Bohr is at a loss to explain why some of these transitions happen more often. When I say, by the way, a hydrogen-like atom, I'm talking about lithium, sodium, potassium, rubidium, cesium, and francium. Cannot explain something called spectral splitting. And under the right circumstances, when exposed to a magnetic field, the atoms of hydrogen, let's just take hydrogen as an example, do not produce those four lines, but instead produce different lines that are splits of those four lines. So in a more general sense, if you get a wavelength in a spectrum that's there, in terms of the location on your diffraction image or interference image, when you expose this to a magnetic field, sometimes what happens is that line goes from this to this. It splits. And neither of those wavelengths corresponds to the wavelength without the magnetic field. Sometimes what happens is, if this is the line that you're observing to begin with, then you get that. So not only does it split, but there's a part of the line that stays there. It's sometimes referred to as Zeeman splitting. And you don't need to know the word Zeeman, but I throw it out there in case you're interested in researching it. And Bohr just is at a loss to explain that. So what's the quantum mechanical model? Here are the key features of the quantum mechanical model. First of all, we don't really attach a name to it. You know, Dalton model, John Dalton. Thomson model, J.J. Thomson. Rutherford, Rutherford. Bohr, Bohr. This wasn't developed by one physicist. It was developed by a group of physicists. You'll sometimes see the name Schrödinger associated with this model of the atom. But we prefer to just call it the quantum model of the atom. So what are the features? First of all, it's not a visual representation. Every model of the atom we've looked at so far is telling you that an atom looks like something. An atom looks like a billiard ball, is what John Dalton says. An atom looks like plum pudding or a ball of chocolate chip cookie dough. An atom looks like a solar system, the Rutherford planetary model. Bohr starts to become less visual because we just draw those lines, but you could say the electron behaves like books on a shelf. That the book can be on this shelf or this shelf or this shelf or this shelf. But I can't just put a book between the shelves and walk away and let it sit there. It has to be in a certain location. The quantum mechanical model of the atom, we don't really have a good representation for what it looks like. I think in Science 10 you might call it the electron cloud model. Does that ring a bell? That the electron exists as a cloud of charge somewhere. That doesn't do it justice. So this is not a visual representation, but it's highly mathematical. And when I say highly mathematical, I don't mean geometric, because geometry is a branch of mathematics that's visual. This is not geometric. It's highly mathematical. It's highly algebraic. In fact, this is from an old physics textbook from university that I have kicking around, and I scanned in the Schrödinger wave equation in polar spherical coordinates, and that's what it is. This wondrous thing here at the bottom, where it says 7.3 in brackets, equation 7.3, that's the Schrödinger wave equation, which can be used to explain the line spectra of any atom. Now, first of all, it looks a little bit like gibberish, doesn't it? There are some symbols in there you're not familiar with. Those of you that take calculus, I could pull this up, if I remember, partway through calculus and go, oh, there seems to be some derivatives in there and some second-order derivatives in there. We'll understand what that means. But the mathematics here is way, way beyond this level. And I just want to point out to you, because I think it's interesting, this equation is complicated, but this is the starting point for any atom on the periodic table. So you can apply this to hydrogen, and out of this comes a whole bunch of other equations that give us the numbers that Bohr had on his energy level diagram. And you can apply this to lithium, and out of it comes a whole bunch of equations and calculations which will give you the energy level values that Bohr predicted lithium would have. But also out of this, you can put in the information for any element, and out of it will come energy level diagrams that match the spectra we observe in the lab, no matter how complicated. And I will tell you that when you apply this to hydrogen, the mathematics is still very, very complicated. But as soon as you go to helium, which is the next most complicated atom, it's got 2 valence electrons. it gets really, really messy, like really ugly. And as I've said before, in 4 years of physics, I only studied hydrogen with this. This whole course was basically, not whole course, but this part of the course, we applied this to hydrogen. And we spent 2 weeks on it probably. We didn't even touch any of the others. So that's what I mean by highly mathematical. So what is it about? What it does, and this is going to seem odd to some of you, that we're coming up with a better theory that explains nature better, explains all of the line spectra for all of those elements, is it doesn't talk about certainties, it talks about probabilities. So where Bohr will say, using the Bohr model of the atom, when the electron has a certain energy, that electron is at a certain radius or distance from the nucleus. The quantum model of the atom will say, well, it might be there, but it might be somewhere else. It seems kind of, in the words of my mom, wishy-washy. It seems like, well, make up your mind, where is it? And the quantum model of the atom deals with probabilities. There's a high probability of it being in a particular location. So if I were to take a look at a graph, and this is a probability as a function of radius graph. Probability, we don't deal too much with probability in the math that you take, but probability is a number from 0 to 1, where 1 is 100% certainty. So if I say, what is the probability that the sun will rise tomorrow? We would say 1. Now, could some cataclysmic event happen to our sun? Maybe, but it's not going to, right? So the probability of a certain event is 1, and the probability of something that's impossible to happen is 0. You can think of 1 as like 100%. This is the Bohr hydrogen model in the n=1 state. So this is Niels Bohr's thinking. This is the radius r1 that I've thrown your way before. And if an electron is in the n=1 energy state, if you said to Bohr, what is the probability that it's at this distance? Bohr would say 100%. It's 1. It's going to be there. It will always be that distance away. But in reality, the probability distribution of where the electron's found in hydrogen when it's in the n=1 state is not that certain. There's some leeway. The electron most of the time is found at this location, but sometimes is found closer to the nucleus, and sometimes it's found further away from the nucleus. But, and this next part is not necessary for this course, but I think some of you might be wondering, it isn't that the electron moves from one place to another. The quantum model of the atom never talks about the electron moving, because it says it doesn't move. It just says it's in one place, then in another place. So there's the Bohr diagram of what the atom physically looks like. This is hydrogen. And here's the quantum mechanical model. You'll notice there's no path, there's no orbit. The quantum model of the atom will say, well, the electron's there, and when we look at it next time, maybe it's there. And then we look at it sometime later, and maybe we see the electron in the atom in that location. And this bit of business just continues on and on and on. And this is where that concept of an electron cloud comes from that you talk about in Science 10. It's like this cloud of charge. But it isn't a cloud of charge, because it's not negative everywhere all at once. It's just negative in a certain place, and then it's negative somewhere else. And if you were to average out these orbital radii, you would discover that it matches that Bohr radius that Bohr predicted. It's really kind of a weird situation, but it is able to accurately predict the line spectra of all atoms. Which is, its crowning achievement, I suppose. It's successful with all atoms. It's very, very complicated, but it works. However, it doesn't just talk about one quantum number. So it isn't just n=1, n=2, etc. for energy levels. There's also a value of a quantum number for something called spin of the electron, something called angular momentum for an electron. There are other quantum states that the electron can be in, and that explains the spectral splitting. let's not worry about this. This is something that is in the curriculum, and it's very confusing, and every time I teach it, I think it just causes more confusion, and I've never seen it evaluated on an exam, and I don't quite know how it could be evaluated. At the end of this lesson, if you like, I will share with you what this is saying, just for those of you that might be interested. But I really mean to exclude it from your notes. It's not important. And sometimes you have to trust me on what's important and what's not, okay? And I admit I'm gambling for you. There could be a question on the diploma exam that asks that, but I think it's very unlikely. All right, so that's the quantum mechanical model of the atom. That's what you need to know about it. Highly mathematical, deals with probabilities and not certainties, and can explain the line spectra of any atom in the universe. Any brief questions on the quantum model? Will?
So with the hydrogen atom we've been looking at and the different energy levels, are those all the valence level? Like if you had an element like lithium that has the valence energy level and then a lower energy level?
No. The question is, what do the energy levels represent for many electron atoms? So in chemistry, you're taught about these. I think you're still taught this. I think you might call them orbitals instead of energy levels. Or do you call them energy levels in chemistry? Energy levels? Okay. Where the first energy level has a maximum capacity of 2. I can't believe I can't remember this. The next is 8. Does it just continue 8, 8, 8, or does it go to 16 at some point?
In Chem 20, you only do 2, 8, and then 2 because you only go up to calcium. That's as far as we go is calcium. So
Oh, I see. Okay.
It's just 2, 8, 8, and then.
Okay. So yeah, and I get it does get quite complicated. There is no one-to-one correlation between those energy levels that you talk about in chemistry, which are really kind of orbitals. Well, I guess they're energy levels, but I'm going to say there's no one-to-one correlation between those energy levels and the E values of 1, 2, 3, 4, 5 for atoms. Because as I understand it, and I'm not a chemistry major, as I understand it, when you look at, say, that second energy level that can hold 8 electrons, there's no difference between, there's no fundamental difference between that energy level in strontium and that energy level in yttrium. I mean, I know there's a difference because the radius will be different, but I don't know that it's a direct correlation to the E values in physics. Okay. I'll leave it with this, and this is a conjecture on my part. I think those energy levels are built on a theory that's much simpler than the quantum model of the atom. So to determine the energy values in physics requires a really in-depth, highly mathematical analysis. But I think knowing about the structure of the atom in terms of them in chemistry does not require that. Ian?
Since the electron's position is determined by probability, it does not have to be exactly on that orbital line.
Correct.
Does that exclude what we just learned in the previous lesson?
Well,
Position.
Yes and no. Maybe I will answer that by saying this graph that I've shown you is highly exaggerated. I've spread it out for visual sake, and it's probably taller and narrower. I think I know what you're getting at, but I will answer it this way. When you apply Bohr's model to predict the line spectra of hydrogen, lithium, cesium, potassium, rubidium, francium, all those, it works. When you apply the quantum model to all of those atoms, the quantum formulas turn into Bohr's formulas. So I don't know if you're asking, do we now not use Bohr's model?
I'm asking, in Bohr's model, it has to, a photon can only be emitted if an electron loses an exact amount of energy, and can only jump to another orbital, another energy level, if it has exactly the same amount of. But if the electrons are not in the exact orbital line, then how can we say that that subtraction and addition is exact?
I don't have an answer for that. I really don't. It's been so many years since I've studied that quantum model of the atom, and I've always been zeroed in on the physics 30 of it. I guess I will say to you that those line spectra seem to be found, and nature seems to use the wavelengths that correspond to this radius or this energy with the maximum probability. But I don't have an answer. And I don't know that I can find an answer, but I will give it some thought. Other questions? And Will, I answered your question, you feel? Okay. Okay, we're going to need our calculators out for this next portion of the class. And I do feel a little bad about not being able to answer your question, Ian, because I don't want it to sound as just an excuse, but it's just literally been so long. And maybe I didn't even understand the answer to that question when I studied quantum mechanics. I don't know that it ever occurred to me. I was probably a young student and just thought, well, I just got to figure out how to solve these equations and get answers. Let me ruminate on it. Think about it. So we're going to go back to Rutherford scattering, and we're going to go back to the Bohr model of the atom and deal with physics principles. And this is a series of questions that are the 1-2 punch physics principle questions. They're going to involve 2 physics principles. The first thing that you're told here is a formula for potential energy between 2 charges. Now, if I go back to physics 20 and I talk about gravitational potential energy, we have a very tidy formula for gravitational potential energy, MGH, right? I want to know the gravitational potential energy of my phone above the floor. I take its mass times the gravitational field strength times the distance between the floor and my phone. Well, it turns out with charge, it's more complicated. If I want to know the electrical potential energy between 2 charges, and the comparison here is the Earth and the phone are masses. Here we're talking about 2 charges. You take Coulomb's constant times the product of the charges divided by the distance. This is not Coulomb's law. There's no r squared there in this formula. This formula is not on your formula sheet. It's not Coulomb's law, and it's not the formula for electric field strength. It's given to you in the question, which it would be on an exam. Q1 is the charge on the particle, Q2 is the charge on the source of the electric field. In other words, Q1 and Q2 are the 2 charges, and R is how far away you are from it. So the first example says, during an alpha scattering experiment, alpha particles are incident on a thin gold foil, and one particular alpha particle has an initial speed of that, and you need to understand that when, in this context, when I say that's the initial speed of the alpha particle, that's the speed of the alpha particle before it's gotten anywhere near the gold nucleus. Just a reminder here, everyone, of what's going on in alpha scattering. In Rutherford alpha scattering, what you have is a gold atom, and there's the nucleus, cartoon-like as it is, doesn't show any protons and neutrons. The electrons are so far away they don't matter, and alpha particles, which are also going to appear to be cartoon-like, are fired randomly at the gold foil. And most of the alpha particles, because there's a very small target, most of the alpha particles do not get very close, but they are deflected a little bit. Some of them, like that one, gets deflected a lot. Some of them, and I don't know if we want to wait long enough, but some of them will be deflected through angles greater than 90 degrees. I'm going to give it 10 more fires. 1, 2, 3, 4, 5. One of those was almost greater than 90 degrees. So that's what's going on in alpha scattering. Now, what this question says is that one particular alpha particle comes back 180 degrees. How does that alpha particle have to approach the nucleus if it's going to come straight back 180 degrees? And we could watch that animation all day and maybe never see it happen. Carly?
Well, it would have to hit it right dead center.
Have to be dead center. And that means it's going to approach and slow down and slow down and slow down and slow down and then change direction. It has to come to a stop. This particular alpha particle, when it gets as close as it can to the nucleus, has to momentarily stop and then change direction. Every other alpha particle never stops. Even if, like that one, it didn't stop, it still had some momentum and motion to the right. And even if you have one that comes back in this direction that I'm indicating, it won't stop as well. It will always have some motion. And this is key to this question, is that what's happening is the alpha particle has a particular speed when it's very far from the nucleus. As it approaches the nucleus, its speed decreases until it stops. And then it's going to bounce back. It never actually hits the nucleus. It just gets really close and bounces back. So another question I have for you. Right here, there's kinetic energy. And over here, there's potential energy. Where did the potential energy come from? Ian?
Storing enough energy by working against the charge.
True. But where was the potential energy before?
In the field.
No. Because that would be potential energy. Well, if you have a pendulum, this is going to be the exact same idea behind a pendulum. If you have a pendulum, and I get this pendulum moving back and forth, at that instant where it touches my nose, and it actually did touch my nose there, at that instant where it touches my nose, that pendulum has all gravitational potential energy. But yet at the bottom it didn't have any potential energy. Where does this potential energy come from? Shannon. It's from the kinetic energy. What's happening is mechanical energy in this pendulum is conserved. The potential energy it has here and the potential energy that it has here are equal to each other, and the kinetic energy that the pendulum has at the bottom is equal to that as well. So the pendulum's mechanical energy is always conserved. As it moves back and forth, all that happens is the potential energy in the pendulum turns to kinetic, which turns back to potential, which turns to kinetic. This is like a pendulum, except it's not going to continue. All this kinetic energy, as the particle slows down, will be lost and turned gradually into potential energy. And what that means is that the potential energy over here has to be equal to the kinetic energy over there. This is a big picture item, or big picture problem. Let's take a look at what the question is asking. How close does the alpha particle get to the nucleus? Well, if the potential energy is at closest approach is equal to the kinetic energy far out, then this 1/2 mv squared will be equal to the kqq over r. That's that new formula. And this is the formula we can use to find R. However, I'm going to put in all of my numbers here. The mass is the mass of an alpha particle, 6.65 times 10 to the negative 27 kilograms. I'm going to leave out the units to make things easier to follow. The speed is 2.6 times 10 to the 7 meters per second. We have to square that. This is equal to k. Well, we all know what k is, right? 8.99 times 10 to the 9 times the charge of an alpha particle, which is 3.2 times 10 to the negative 19 coulombs, times the charge of a gold nucleus. Well, you're going to learn starting tomorrow something that you're probably taught in Science 10 and somewhere along the way in chemistry as well, that the atomic number of an element, like zinc is 30, copper is 29, boron is 5, lead is 82, the atomic number always tells you how many protons are in the nucleus. So when we find gold, well, that's funny. I mean, I know what it is. I guess I'll just... Where is it? You guys are just going to let me sweat away, aren't you?
It's AU.
I know it's AU. I just can't... There it is. I just couldn't find it. 79. Gold is atomic number 79, and that means that the charge of the nucleus is 79 elementary charges. It's 79 times 1.6 times 10 to the negative 19, because 79 means there's 79 protons in the nucleus. And the charge on the proton is what gives the nucleus its charge. Over R, so we want to find R. When I rearrange this, I'm basically going to cross multiply to move the R on the top of the left side. So if I take KQQ and divide by this energy, I'll get the answer. In other words, I'm going to calculate this energy and divide KQQ by it. So what is the kinetic energy? 0.5 times the mass, 6.65, multiplied by 10 to the negative 27 times that speed. Can you just verify that that speed is correct? 2.6 times 10 to the 7. Okay. Squared. This is the kinetic energy in joules that the alpha particle has before it starts to transform its kinetic energy into potential, which means this is the potential energy, which is KQQ over R. So I have to take K multiplied by the charge of an alpha particle multiplied by the charge of a gold nucleus. And I'm just entering that in as 79 times 1.6 times 10 to the negative 19. I don't think I need to calculate what that number is and then write it down. And then divided by that energy gives me this distance. 1.6 times 10 to the negative 14 meters. That's how close it gets. And by the way, it's through these analyses that Rutherford was able to determine how small the nucleus is. Any questions with the calculations on that example? All right. During an alpha scattering experiment, alpha particles are incident on a thin gold foil. One alpha particle has that initial speed. So this is the second question relating to that. It says, what's the maximum acceleration? Now, when the alpha particle gets here, it will be stopped. But it's at that point that the force pushing it backwards is greater than anywhere else. Because Coulomb's law says that the electric force is equal to KQQ over R squared. This is from Unit 2. And since this is the smallest approach, the smallest distance, the force on the alpha particle will be as great as possible there, and that's where the acceleration would be as great as possible. The maximum acceleration, which is what we're asked for here, will correspond to the maximum force, which corresponds to the minimum distance. So what we can do is use Coulomb's law along with this distance we found to find the force repelling the alpha particle at that point, and then set it equal to ma. So what we're going to do in the second question is essentially say that the net force is equal to the electric force, which means ma of the alpha particle equals kqq over r squared. And again, if we use a minimum r, we get a maximum acceleration. So now what I need to do is calculate this kqq over r squared and divide by the mass. And that will be the acceleration at that point. So k is 8.99 multiplied by 10 to the 9 times the charge of an alpha particle, which is 2 elementary charges, times the charge of the gold nucleus, which is 79 elementary charges, divided by my answer squared. And this is going to be the force in newtons. Just want to double check my entries. I think it looks okay. Nope. Now it looks okay. Does anybody else get 139 newtons, roughly? Think about that for a second. That's a huge force. 139 newtons is the force required to lift roughly 14 kilograms, which is about 35 pounds. Maybe not quite 35, but it's 30 to 40 pounds. To give you a rough idea of weight, in case you're not familiar with weight, but 30 to 40 pounds, if you had to carry that around all day, that's a huge weight. One of those 5-gallon water jugs, those blue water jugs, when it's full of water, is 45 pounds of water. So imagine it 2/3 of the way full and you're going to carry it around all day. That's the force being applied to this tiny alpha particle. It's huge. If I divide that now by the mass, I get a phenomenal acceleration, 2.1 times 10 to the 28 meters per second squared. I'm going to pause there. Any questions with that set of calculations? So you need to understand something. I could have given you this information and asked you question 2 without asking you question 1. You would have to be crafty enough to go, well, I need to know the distance of closest approach, so I'm going to use conservation of energy. We used conservation of energy to answer this question, but we used physics principle 1, or accelerated motion, to answer this question. So now if we put it all together, during an alpha scattering experiment, one alpha particle experiences a maximum acceleration that's given to you. It's deflected back 180 degrees, which means that EK far away equals EP closest That's because it's 180 degrees for deflection. It has to come to a stop and then come back. What is the maximum speed that the alpha particle would have had? Well, the maximum speed is going to be connected to the maximum kinetic energy. This is 1/2 mv squared. This is kqq over r, not r squared because this is energy. So if I said to you, find that speed, you're missing something. What are we missing that's stopping us from finding the speed in that formula that we just made? Ian? The radius, the distance, right? And that's the distance of closest approach. We don't need to make a note of this to solve this equation that I've got, but that distance is the smallest distance. And that smallest distance corresponds to the maximum acceleration. It's when the alpha particle gets as close as possible to the nucleus that it's repelled as much, the most amount. And that means that we can say F net equals Fe and have mass times the maximum acceleration equals k times q over the minimum distance squared. So the big picture. Students who are successful in Physics 30 are going to be the ones that understand the big picture. You're not going to memorize a bunch of formulas here. Notice in my energy formula, it's kqq over r, and in my force formula, it's kqq over r squared. So what we need to do is find this first, so we can take whatever number it is and put it in here to find the answer to the question. When I look at this, I'm going to have to take kqq over ma and then take the square root. Just briefly, if ma equals kqq over r squared, then when I cross multiply, I get mar squared equals kqq, which means r squared equals kqq over ma. So I need to do kqq over ma and take the square root. K is 8.99. Multiplied by 10 to the 9 times the charge of an alpha particle times the charge of the gold nucleus. Now I need to divide by the mass of the alpha particle, and I need to divide by the acceleration. Can you tell me, please, Carly, what was the acceleration in this question? Can you look at it?
Yeah, 3.55 times 10 to the 19.
Excellent. Divided by 3.55 times 10 to the 19. We've been down similar roads before. When you have lots of calculations, just make sure you've entered everything correctly before you hit equals. K, Q. Yeah, that's not right. I gotta. K, Q, Q. Better now. Okay, and that goes to show you right there. Double check. What we're finding here is not r, it's r squared. So I have to take the square root of the answer. Now I know what r is. The distance of closest approach for this particular alpha particle is 3.9 times 10 to the negative 10 meters. Now I need to use that to find the potential energy. So this is my K times the charge of the alpha particle times the charge of the gold nucleus. I have to divide by my answer. I'm finding energy, so it's not R squared, it's just R. That's that formula you're given for all of these. So this is the energy, the potential energy that it has at the distance of closest approach, which means it's the kinetic energy that it has when it's moving as fast as possible. So I need to multiply that by 2, divide by the mass, and take the square root. About 1.7 times 10 to the 5 meters per second. Anybody else get the same number? Okay. Any questions with that example? Okay, we essentially have one more example, and I know there's more examples there, but my notes have changed, and I just didn't have time this semester to change this portion. It's why I only gave you the first half of the unit, and you'll get the second half tomorrow. Okay, I want to do a better job on the next one. We're not going to do 5 and 6. And I don't even want to discuss why. They are related to the challenge problems in the assignment. We are going to look now at number 7, and then we will be done. There's another question that we're not going to do. Okay. First of all, in number 7, can you confirm that your 7 says the speed of an electron in the 4th Bohr orbit of hydrogen? It says 3rd? Okay. Okay, so we are asked to determine, and this is a classic question that you need to know how to do. We are asked to determine how fast is an electron moving when it's in the n equals 3 energy level of hydrogen. And you are actually told the formula to find the radius of any energy level. So if you put in 3 into this formula, you'll find R3, and we're going to need to do that in a bit. The first thing to note is that the energy values on your energy level diagrams are not kinetic energy, they're kinetic and potential. You cannot take an energy on that diagram, that energy level diagram, and apply it to answer this question. What you have to do is say that the net force equals ma, but the electric force is kQq over r squared, and they are one and the same. The electric force pulling on an electron in a hydrogen atom is the net force. What we're talking about here, everybody, is here's the proton in hydrogen, here's the electron moving in a circular orbit. Yes?
Should that be r squared because it equals?
Yes. Thank you, Carly. It should definitely be r squared. So ma is equal to kQq over r squared. You did this last year with satellites, except it was ma equals gmm over r squared. This is centripetal, and we've done the same thing with magnetic forces, haven't we? So this becomes mv squared over r equals kQq over r squared, and we have enough information to answer the question. You're asked to find the speed. Do you know the mass of, this is an electron in orbit. We're done with alpha particles here. Do you know the mass of an electron? Yeah. Do you know Coulomb's constant? Do you know the charge of the electron? Do you know the charge of the nucleus, which is a proton? What don't you know? Jack, what do we need to find here first? Well, we're radius, r, the distance, the radius of orbit. But Rn is n squared r1. You're given that little nugget of information. So if we want to find R3, because it's in the 3rd energy level, R3 is equal to 3 squared times R1. I'm pretty sure I know this, but can you confirm that R1 is 5.29 times 10 to the negative 11? Thank you, Caden. 5.29 times 10 to the negative 11 meters. So all we have to do, and by the way, let's just make our lives a little bit simpler by canceling an R from both sides. Life is hard enough. So what we need to do is take this, put it in here for R, calculate KQQ over R, solve for V, divide by the mass and take the square root. And just so you know, the problems you're going to be practicing today are all these alpha scattering problems and this kind of question. Three squared is 9. Nine multiplied by 5.29 times 10 to the negative 11 meters. So this is the radius of the electron's path in the third energy level. Take K times the charge of an electron times the charge of a proton. Again, this is not alpha scattering. This is just the hydrogen atom. Divided by that, this is giving me mv squared. So now I need to divide by the mass. It's an electron that's accelerating in a circular path, and then take the square root. So it's about 7.3 times 10 to the 5 meters per second. I think you probably have a number 8 there as well, but that's one of the ones that I want to omit from my note package. I think that goes a little bit too far. So all of these problems are related to all of this stuff. Question 1 and 2, 3, 4, 5, 6, 7, 8. I think there are some challenge problems like maybe 10 and 11 or those involve situations, just in case you're curious, where the alpha particle approaches the gold nucleus but is deflected at an angle, which means it never stops. Which means over here where it's got kinetic energy, that kinetic energy will be equal to over here, kinetic and potential. And that's just going too far.